Okay, let's go. We've got the second derivative test now. The second derivative test, as I put in quotes here, is another way to find relative extrema on f, on the original function. I'm going to also preface it with this. Some teachers love this theorem. I don't love it. You should only be using the second derivative test when asked to use it, or number two, if the first derivative test does not work well. That usually happens down the road when it's just hard to figure out where the first derivative test changes signs, right? So I want to be very clear on that. Okay, let's dive into it. If f prime of c equals 0, such that x equals c is some real number and f is concave down at x equals c. All right, let's write out what that looks like. So if you've got f prime of c equals 0, that means f has some kind of horizontal tangent and you're concave down at that c value. Let's draw it right here. Then we've got a horizontal tangent line at that point at x equals c, as well as we've got concavity facing down. What kind of relative extrema occurs at x equals c? That'd be a relative maximum, right? Just looking at the picture, just draw it out. Right? You don't have to memorize this test. Draw it out in your head. Derivative's got to be 0, okay? And if it's 0 there, then the second derivative being concave down, well, the second derivative here would be negative, then we have ourselves a relative max. Too many students memorize this. They say, if the derivative is 0 at an x value and I plug that into the second derivative and I get a negative value, then I've got a relative max. Don't memorize it, see it. Horizontal tangent line, if you're concave down there, right, you're going to have a relative maximum. Imagine that. Very cool. And I guess what I'll do is I'll neaten up this notation. We could write that as f double prime at c, because that's really what we're looking at. And of course, we'll put this into motion with numbers. If f prime of c equals 0, okay, so we got a horizontal tangent line at some value, and f is concave up. All right, so we got something like this. Here's c. F prime at that point is equal to 0. Then what kind of relative extrema occurs? A relative minimum occurs at c. And f prime at this point is going to be concave up. So f double prime of c is greater than 0 since f is concave up there. That's it. That's your second derivative test. So then how do we use it? How do we use this knowledge? Well, let's put it to work. Now, keep in mind, by the way, the test fails if the second derivative ever equals 0 at a point, right? Because then we don't know what the concavity is, and then you'd have to use the first derivative test anyway. So I'm going to go through the second derivative test here, but then also show you how the first derivative test supports us. So to use the second derivative test, we still have to find our critical numbers, our places where this curve has horizontal tangents. So I take g prime of k, apparently, is equal to 12k to the fifth. Don't know why I went with k there. Minus 12k to the third. We still set that equal to 0 because we are interested in the critical values. So set it equal to 0. GCF, you're out of there. 12k cubed. That's going to leave us with a k squared minus 1 equal to 0. So our critical numbers, there's 3 of them. You'll have one at k equal to 0. And k squared minus 1 equal to 0 would have 2 values, negative 1 and 1. Now, I prefer going with your first derivative test here, doing a sign chart of that and just ending it. All right? But the second derivative test goes a little bit further. So we now have these values. Now we take a second derivative. And we're going to test the second derivative at these critical numbers to see what the concavity is doing there. So g double prime of k, the derivative of the first derivative, is 60k to the fourth minus 36k squared. Okay, now what we're going to do is we'll test these critical numbers. We know that at these points we have horizontal tangent lines. So do we have something that goes like this or something that goes like this? Again, the test fails if the second derivative is 0. So I do g double prime at 0. Oh, the first one we plug in, that's equal to 0. So the test fails. So we're actually going to have to use the first derivative test anyway. This is why I think the second derivative test is so ridiculous. But it's still cool to understand it. G double prime of negative 1, we'll plug that in. That's equal to, actually, we don't even really care what the number is, but G double prime would be 60 times negative 1 to the fourth minus 36 times negative 1 squared. All I care about is that total expression is going to be greater than 0. Why does that matter? Well, that means that we're concave up where the horizontal tangent line was 0. So, therefore, we've got a relative minimum, right? Remember, horizontal tangent line, concave up at negative 1. at x equals -1. Now we'll plug in that value to find out what the y value is. So -1 to the 6th is 1. So we're just doing g of -1. Times 2 is 2. Minus 3 times essentially 1 is what you get when you plug in -1. So 2 minus 3 is -1. So that's at x equals -1, y equals -1, or the point -1, -1. Okay, let's test it again. G double prime at 1 now. Well, that's going to be equal to 60 minus, minus, we're using the second derivative, minus 36, which again is greater than 0. So we're concave up. We got a horizontal tangent line, concave up. So we again have a situation like this. And that would therefore be a relative minimum at x equals 1. Now, what is the point there? G of 1, it's going to be actually the same point. It'll be still 2 minus 3 when all the dust settles. It's the same y value, I should say. So, relative minimum at 1, -1. Now, what about g double prime equaling 0 there? It failed. We didn't know the concavity. Well, we got to do more with that, and that's the pain of this test. So, I look at my number line, and I know my critical numbers were -1, 0, and 1. So I've got to test points around 0. Right? Let's test them all while we're here. So below -1, we're testing the derivative here because we're, again, looking for relative maxes and mins on G. So I'm going to plug in a value less than -1, -32 billion. Cubed is negative, still negative. Squared minus 1 is positive, so the whole thing's negative. 1/2, so -1/2. Cubed is negative. Squared is a number less than 1, so that's a negative and a negative. That's a positive. There we go. We had a relative min. We already knew that, right? We went from negative to positive to get a relative min on the first derivative. How about to the right of 0? We'll plug in 1/2. Cubed is positive. Squared minus 1 is negative. Again, testing 1/2 gives us a negative. And we then, therefore, have a relative max at. And that's going to be at x equals 0. Plug it in and you'll get 0. So we got a relative maximum at 0, 0. That's via the first derivative test. Let's plug in another point. A value greater than 1 on the first derivative, 32,000. Plug that in the first derivative. Cubed, positive. Squared, minus 1, still positive. So G goes from decreasing to increasing to decreasing to increasing, which just tells us what we knew from the second derivative test, a relative min, right? Decreasing and increasing, increasing and decreasing, decreasing and increasing, and another relative min here at 1. I would much rather have just done that. You find the same conclusions. But again, I think it's important to know this test, understand how it works and why it works, and see that it does fail when the second derivative is 0, and then you have to rely on the first derivative test anyway. All right, but know this and know it conceptually. Don't memorize it. That's all I got for you here. I'll see you in the next one.